Hey, math enthusiasts! Ever heard of the notorious Baby Rudin? This textbook is famous, or infamous, for being a challenging introduction to real analysis. Rudin's Principles of Mathematical Analysis, affectionately nicknamed Baby Rudin, is a classic textbook for learning real analysis. Some students swear by its clarity and rigor, while others find it difficult and lacking in motivation. Today, on the Academy of Useless Ideas, we are diving headfirst into the first 2 pages of Baby Rudin. We'll use this as a springboard to explore Rudin's writing style, uncover a surprising but ultimately unimportant mathematical fact, and most importantly, equip you with tips for tackling tough math textbooks. Whether you wrestled with these pages yourself or are just curious about what the fuss is about, feel free to pause the video and come back once you've read the pages. We'd love to hear your thoughts in the comments below. So what exactly happens in these first 2 pages? Rudin dives straight into a foundational question for calculus. What kind of number system do we need? He argues that the familiar fractions, the rational numbers, aren't quite good enough. Here is the twist. Even though you can always find another fraction between any two you pick, there are gaps such as the square root of 2 lurking within. So why are those gaps problematic? Unfortunately, Rudin doesn't tell us why those gaps cause problems for calculus. This implicit style is a hallmark of Rudin. Unlike some textbooks that hold your hand, Rudin expects you to figure things out yourself. This can be challenging, but that's why we are here. Before we crack open these first 2 pages, let's hear from you. What are your initial thoughts on Rudin's approach? Any burning questions? Got any strategies for tackling tough math textbooks? Share your thoughts in the comments below. So, how does Rudin expose these sneaky gaps in the rational numbers? After revisiting the classic proof of the irrationality of 2, he dives deeper into this phenomena. His conclusion: you can create 2 lists using fractions. List A has fractions whose squares fall short from 2, and list B has fractions whose square zooms right past 2. The weird part? List A never reaches the biggest member, and list B never gets a smaller one. Now, these specific lists might seem like a random detour, but there is a method to Rudin's madness. The key takeaway is that a whole, such as the square root of 2, splits the rational numbers in 2 sets, one of them without the largest element, and the other one without the smallest element. Later in the book, Rudin will exploit this idea to construct the real numbers. However, one could argue that he could have provided more hindsight to the reader. Alright, dear friends, before we delve deeper, let's pause and dissect this result Rudin throws our way. Remember, active reading is key, so grab a pen and paper or your favorite note-taking app and take a crack at understanding these whole rational number gaps. For such exercise, we propose 3 strategies. First, make it personal. How would you explain these weird number gaps to your grandma or whoever you think might be utterly confused? Second, think outside the box. Can you restate the result in multiple ways? Third, why should we care? Is this some random mathematical quirk, or is there a deeper reason why these gaps wreak havoc on calculus? Let's see your best explorations in the comments below, or head over to our Discord server to brainstorm with the Academy of Useless Ideas crew. Relying on these strategies, we can grasp better Rudin's result by expressing it as follows. For every rational number p, there exists another rational number q that is in closer proximity to the square root of 2 whole. We'll break down this concept into two scenarios, one where p squared is less than 2, and another where p squared is greater than 2. In the initial scenario, our goal is to identify a q larger than p, ensuring that q squared remains less than 2. Take a moment to consider the requirements for the second scenario when p squared exceeds 2. If needed, pause the video and resume once you've formulated an answer. Engaging in this exercise of anticipating someone else's reasoning is a valuable strategy to enhance your critical thinking skills. Upon reflection, you might concur that when p squared surpasses 2, our objective is to find a q smaller than p, yet q squared must still exceed 2. Do you align with this objective? Or do you have any inquiries about it? Remember, unlike reading a textbook, you can rewind and ask questions. So don't be a wallflower. Leave a comment below if anything is confusing. Your questions help us create even better explanations. We are finally ready for the tricky part. How do we find this special fraction q that gets us even closer to that pesky square root of 2? If you feel adventurous, take a break to find a solution yourself. If your initial guess is different than Rudin's solution, do not fret. We would be delighted to see your solution in the comments section. After all, some math problems, like this one, have multiple answers. Rudin throws a fancy formula our way for this mysterious q. It involves some jiggling with our original fraction p and some pluses and minuses. Don't fret, we don't need to memorize such formula. What matters is whether this formula actually delivers a q that gets us closer to our target. Let's check first the case in which p squared is smaller than 2. Remember how we needed a q that lands a bit closer than our first attempt, where p squared is less than 2? Well, with Rudin's formula, we can see that q is basically our original fraction p with a tiny positive notch. This should definitely get us closer to the square root of 2. But there's another hurdle. We need to make sure q doesn't zoom right past our target, meaning q squared needs to be less than 2. Here is the cool part. The math checks out. As long as our original guess p wasn't too far off, p squared is less than 2, this formula ensures our second attempt q lands safely in the zone. Before we continue, are you feeling lost in the math maze? Hey, no worries. Leave a comment below if this verification step had you scratching your head. We are here to help. On the other hand, if you find that step clear enough, then take on the challenge of proving the second case in which p squared is larger than 2. We won't hold your hand on this one, but if you are curious for a more detailed breakdown, head over to our Discord server. Alright folks, let's take a break from calculations and delve into the real head scratcher. How did Rudin pull that q formula out of his mathematical hat? This one had me stumped when I first slogged through Baby Rudin. Honestly, I just gave up and figured Rudin played mathematical whack-a-mole with equations until something worked. Amusingly, knowing where this formula came from doesn't magically make you an analyst whiz. But as math enthusiasts, we crave understanding. When a proof looks like a magic trick, you gotta wonder if there's some sneaky sleight of hand happening behind the scenes, right? Mathematicians love to present proofs as clean and polished as possible. But that can hide the blood, sweat, and maybe a few tears that went into figuring them out in the first place. So, what do you think? Should mathematicians spill the beans on how they conjure up these proofs? Or is it okay to keep things concise and let the final product take center stage? Leave a comment below and let's get this philosophical math debate rolling. While you discuss these issues, let me tell you, contacting Rudin through the mystical powers of the Ouija board about his Q formula proved, well, ineffective. But fear not, because yours truly spent a good chunk of time banging my head against this wall, mathematically speaking, and well, let's just say while digging into the world of Pythagorean triples, a solution Q kinda popped into my head. Maybe it was luck. Maybe it was the fumes from all the brain power expended. Who knows? But before we delve into this happy little accident, let's take a pit stop in the land of Pythagorean triples. These are triples of natural numbers that can form the sides of a right triangle. For example, think of 3, 4, 5. The coolest part, there are infinitely many of these geometric goofballs, and there is even a secret recipe to cook them up, Euclid's formula. This formula lets you grab any two whole numbers and bam, a Pythagorean triple is born. Pretty neat, right? But how, you ask, did some ancient math whiz stumble on this magical recipe? Should we dust off our Ouija board to find the answer from Euclid himself? A mathematician may invest years in grappling with a problem, and upon solving it, she can distill the essence in just a couple of hours. This remarkable efficiency in transferring both effort and information allows us to stand on the shoulders of giants like Euler and access knowledge even they couldn't dream of. While it would be immensely enjoyable to rediscover every intriguing result, such an endeavor is impractical. Nevertheless, it remains worthwhile to ponder problems for a brief period before seeking the solution. Take a short break, perhaps go for a walk, and when ready, resume the exploration for the derivation of Euclid's formula for Pythagorean triples. Firstly, note that Pythagorean triples must satisfy the Pythagorean theorem, where a squared plus b squared equals c squared. Generating triples of real numbers satisfying this equation is straightforward. The difficulty lies in finding solutions in which a, b, and c are natural numbers. To simplify the problem, we divide the Pythagorean equation by c squared and substitute a over c for x and b over c for y. These algebraic manipulations allows us to focus on finding a solution to x squared plus y squared equals 1, where x and y are rational numbers. Although it may seem like we haven't made much progress, reducing the equation to two variables, namely x and y, enable us to plot the points satisfying this equation in a plane. If this were the real plane, each point in the unit circle would represent a real-valued solution. But let's not forget that we are only interested in rational solutions. So how can we ensure that we select only rational numbers? The key lies in this simple idea. Picture a straight line passing through the points -1, 0, with a rational slope represented by t. The equation of such a line is y equals t times x plus 1. Now, hit the pause button, glance at the unit circle and the line. What revelations can you draw from this visual aid? What nuggets of information might aid us in our mission to discover Pythagorean triples? This practice of keen observation and contemplation is the bread and butter of mathematicians. Admittedly, in this scenario, we are benefiting from hindsight. Consider the countless diagrams, equations, and potential paths a mathematician navigates before striking gold. It's the reason we invest substantial time in deriving results that, once uncovered, can be articulated with far greater brevity. As we build the line, it naturally crosses the unit circle at the coordinates -1 and 0. Now take a note. There's another meeting point between the line and the circle, and we'll dub it P. So what's the scoop about this mysterious P? Here's the deal. If P happens to be a rational point, we strike gold with a solution to our problem. Now the million-dollar question. Are both coordinates of P rational or not? Ponder on that for a moment. If P turns out to be rational, we are in business. We can solve a system of two equations and crack the code. But hold on. Why would P even be a rational point? Any hunches on this one? Let's the wheel of contemplation spin. I am no stranger to the feeling of being stuck when I can't find an answer. I have this itch for every step to be rock solid and irrefutable. This craving for control tends to hold me back from venturing into uncharted territories. But hey, every now and then, we've got to channel our inner race car driver. As the saying goes, if everything seems under control, you are not going fast enough. Buckle up, let's tackle these two equations and hope this daring approach speeds us to victory rather than slamming us into a wall. After plugging in y's value from the line equation into the unit circle equation and simplifying the result by factoring x plus 1, we uncover the gem that x equals 1 minus t squared over 1 plus t squared. Once we have our hands on y, the revelation strikes. Y turns out to be twice t over 1 plus t squared. Voila! Lucky us, right? It's like hitting the rational jackpot because when t is a rational number, both x and y tag along as rational sidekicks. But hold on a second. We are not believers in mathematical coincidence. So, let's dive into the why behind this stroke of rational luck. Any theories? Share your wisdom in the comments or on Discord. Now for the grand finale. We jot down the slope t as n over n. Then, with some algebraic wizardry, we unveil the magical return of Euclid's formula. There is a whole universe of Pythagorean triples and their secret connections to other mathematical mysteries. Go on, ponder on these problems. Drop your questions or musings. Your brilliant insights are the spark for new videos and discussions. Maybe, just maybe, one day we'll delve deeper into Pythagorean triples. But for now, let's flip the script back to the second page of Baby Rudin. Let's jog our memory. Given a rational number p, our quest is to unearth a rational number q, snuggling up closer to the square root of 2 than p. We've validated Rudin's equation for q, but the mystery remains. How did Rudin conjure up such an equation? Now that we've dabbled into the world of Pythagorean triples, do you have any bright ideas for crafting a similar equation for q? Before we continue, let's take a time out to ponder a famous quote by Seneca. It's not that we have a short time, but that we waste much of it. Now, the Academy of Useless Ideas isn't entirely solid on the whole wasted time thing. After all, getting lost in a math problem can be way more fun than consuming your life in a soul-crushing job. Here's the thing. The journey of discovery in math is often way cooler than just knowing the answer. Think of it like a choose your own adventure math story. So, if you're feeling the urge to take a break and explore this problem on your own, no worries. We'll be here when you get back. Of course, if you already figure out the answer, or you just want to buckle up for the ride, we are happy to have you along. There are always new math problems waiting to be explored after all. Math is like a never-ending buffet of brain teasers. You just gotta find the ones that tickle your fancy. Let's borrow a page from the Pythagorean Triples playbook. But this time we are trading the circle for the parabola y equals x squared minus 2. Our starring players in this parabola drama are the points 2, 2 and p squared minus 2. Regardless of where p takes its stand, the line's rendezvous with the x-axis yields a point q. Now note that this point q seems to cozy up quite snugly to the square root of 2. Could this be the enigmatic point that Rudin stumbled upon? Surprisingly, the quest for pinpointing this elusive point q leans heavily on sketching a few illustrations rather than being drowned in a sea of equations. Sure, we'll dip our toes into some algebraic maneuvers to whip up an equation for q and validate its coveted properties. Admittedly, the algebraic grind can be a tad tiresome, but fear not, it's all in service of preserving our geometric gut feelings. This whole endeavor brings to mind a witty quip. Algebra is the offer made by the devil to the mathematician. The devil says, I will give you this powerful machine. It will answer any question you like. All you need to do is give me your soul, give up geometry, and you will have this marvelous machine. But let's not get too dramatic. The deal isn't necessarily Faustian. We need not relinquish geometry to embrace algebra. In fact, here is a spicy take. Forsaking your intuition in favor of mindless symbol pushing, surrendering your soul, is a breeding ground for the unsightly, worthless mathematics clogging up the world's archives. What's your take on this philosophical math dilemma? Alright, dear friends, here is the big reveal. Our fancy picture-based approach to point Q actually matches the one in Baby Rudin. Who knew a little doodling could be so powerful? Now, whether Rudin himself used this method or some other mathematical magic trick, we'll probably never know. But hey, that's the beauty of math, right? There is often more than one path to solve a problem. And speaking of different paths, guess what? While pondering about this problem, I stumbled upon another formula for Q that also fits the bill. Picture this other solution. Q equals 3p plus 4 over twice p plus 3. The question is, can you detectives out there figure out if this new formula works its magic? And bonus points if you can guess where I got this formula from. Hint, it has something to do with our crazy proof for the irrationality of 2. If you are curious to dive deeper, feel free to leave a comment below or hit us up on Discord. Let's crack this mathematical code together. As we wrap up, let's revisit the primary objective of Baby Rudin's initial pages. To convey that he embarks on his mathematical journey from the realm of rational numbers, even though this number system isn't the most conducive for analysis due to the presence of gaps like the infamous square root of 2. Our discussion today delves into a specific result related to these gaps. However, it's worth noting that most of what we explored here isn't mandatory for comprehending Rudin's overall argument. If it feels a bit dense, don't be disheartened. Baby Rudin tends to grow on readers as they progress in their studies. Before diving into analysis, most folks think of math as a giant recipe book. Follow the steps, solve the problems, boom! You learn how to translate problems into equations, then wipe out a procedure to solve them. That's why most elementary math books focus on what problems you can solve and the exact steps to get the answer. Think of it like learning an algorithm, identifying the problem, plug it into the formula, voila. But analysis? Analysis is all about ditching the recipe book and exploring the beautiful structures of math. There are fewer procedures to memorize, but tons of concepts to wrap your head around. This shift in perspective can be a mind bender for sure. When you crack open those first few pages of Rudin, you might expect a problem, then a magic formula to solve it. Instead, you get smacked with a fact about rational numbers. They have gaps. Then Rudin throws this example at you to explore the idea, but it's not exactly a typical problem you can solve with a fancy formula. The example is there to shine a light on a concept, not to give you a step-by-step solution. So there you have it, adventurers. We may not have cracked the entire code of Baby Rudin just yet. But hopefully this detour through Parabola Land sheds some light on the fascinating world of analysis. Remember, in analysis, the focus is on exploration, not just following a recipe. So don't be afraid to ask questions, experiment with different approaches, and even get a little lost along the way. That's often how the coolest discoveries are made. Before we go, what do you think of those 2 pages now? When you first read them, did they seem important, or did you just kind of gloss over them? Did this video help you, or are you feeling lost in the wilderness of math? Don't worry, we've all been there. Join our Discord community, link in the video description, to connect with other math explorers, share your struggles, and celebrate your victories. The road to mathematical mastery is long, but together we can make it a fun and unforgettable journey.